Pressure can build for centuries in places that appear outwardly still, accumulating silently beneath landscapes that show little sign of movement. When that stored energy is finally released, even a region considered stable can produce a seismic event strong enough to raise questions far beyond its immediate impact. How does a magnitude 5.5 earthquake emerge from the interior of a continent, often described as geologically quiet? Why do such events occur, far from the dramatic plate boundaries that dominate global seismic activity? And what does it reveal about the hidden architecture beneath one of the oldest landmasses on Earth? A magnitude 5.5 earthquake has been recorded in central Australia, a region not typically associated with frequent or large seismic events. The epicenter was located roughly 77 kilometers south-southwest of Ulara, placing it within a remote section of the Northern Territory characterized by arid terrain, sparse population, and deeply ancient geological formations. Despite its isolation, the event has drawn attention due to both its strength and its location within the interior of the Australian plate, far removed from the tectonic boundaries where earthquakes most commonly occur. Initial seismic readings indicate that the earthquake originated at a depth of approximately 10 to 11 kilometers beneath the surface, positioning it firmly within the brittle upper crust. At this depth, rocks are capable of fracturing and slipping suddenly when subjected to sufficient stress. The magnitude suggests a moderate release of energy, enough to generate shaking that could be felt across a wide area, particularly given the efficiency with which seismic waves travel through the rigid old crust of the Australian continent. In stable continental interiors, such waves often propagate over greater distances compared to regions with more fractured or heterogeneous geology. The location of the earthquake places it near a complex geological boundary between the Musgrave Block and the Petermann Ranges. These formations are not active plate boundaries, but are instead remnants of ancient tectonic processes that shaped the continent hundreds of millions of years ago. The Petermann orogeny, which occurred approximately 500 to 550 million years ago, played a significant role in deforming the crust in this region. During that period, immense compressional forces caused large sections of the crust to fold, fault, and thicken, creating deep structural features that persist to this day. Although these structures are no longer actively forming mountains or reshaping the landscape in dramatic ways, they have not disappeared. Instead, they remain embedded within the lithosphere as zones of mechanical weakness. Over geological time, these weaknesses can be reactivated when stress conditions become favorable. The Australian plate, while often described as stable, is not free from stress. Forces generated at distant plate boundaries, including interactions along the edges of the Indo-Australian plate, are transmitted across vast distances. These stresses accumulate slowly but persistently within the interior of the plate. In this case, the earthquake is believed to have resulted from the reactivation of one of these ancient, deeply buried faults. Unlike well-known fault systems such as those found along plate boundaries, faults in intraplate regions are often difficult to identify. They may not produce visible surface expressions, and their traces can be obscured by erosion, sediment cover, or the sheer age of the terrain. As a result, there is no clearly mapped surface-breaking fault that can be definitively linked to this event. Seismological analysis provides insight into the nature of the faulting through what is known as a moment tensor solution. This mathematical representation describes how the fault moved during the earthquake. In this instance, the solution reveals two possible fault planes, referred to as nodal planes. One plane is oriented roughly north-northwest to south-southeast with a moderate dip, while the other strikes southeast to northwest with a steeper inclination. Both orientations are consistent with the regional stress field, and without additional data such as a detailed aftershock distribution or direct surface observations, it is not possible to determine with certainty which plane represents the actual fault that slipped. The motion along the fault is characterized by rake angles of approximately 108 degrees and 78 degrees for the two nodal planes. These values indicate that the earthquake was dominated by reverse faulting. In such a scenario, one block of crust is pushed upward over another as a result of compressional forces. This type of movement reflects a tectonic regime in which the crust is being shortened horizontally. Rather than sliding past one another or pulling apart, the rock masses are being forced together, leading to vertical displacement. Further evidence of this compressional environment is provided by the orientation of the principal stress axis. The axis representing maximum compressive stress, known as the p-axis, is nearly horizontal, indicating that the dominant forces are acting laterally across the crust. The axis representing extension, or the t-axis, is steeply plunging, consistent with a setting where vertical movement accommodates the horizontal compression. This configuration aligns with observations from other intraplate earthquakes in Australia, suggesting a consistent pattern of stress distribution across the continent. The absence of a surface rupture is not unexpected for an earthquake of this magnitude and depth. The rupture likely extended over a distance of only a few kilometers, confined entirely within the subsurface. While this limits the potential for visible ground displacement, it does not diminish the significance of the event. In fact, earthquakes in stable continental regions can be particularly notable because they occur in areas where seismic hazard is not always fully appreciated. Reports of shaking, where available, are expected to cover a broad area, potentially extending hundreds of kilometers from the epicenter. The efficiency of seismic wave propagation in old dense crust allows energy to travel with relatively little attenuation. This means that even moderate earthquakes can be felt far from their source, sometimes surprising populations that are unaccustomed to seismic activity. However, given the remote location of this event, the immediate impact on infrastructure and communities is likely limited. From a geological perspective, the earthquake highlights the enduring influence of ancient tectonic processes. The structures formed during events, such as the Petermann and Alice Springs orogenies, continue to shape the mechanical behavior of the crust. These inherited features act as focal points for stress accumulation and release, effectively serving as the hidden framework within which modern seismicity occurs. Even though the forces that originally created these structures have long since ceased, their effects remain embedded in the fabric of the continent. The Australian plate itself is moving slowly northward at a rate of several centimeters per year, interacting with neighboring plates along its boundaries. These interactions generate stresses that are transmitted inward, where they encounter the complex network of ancient faults and zones of weakness. Over time, these stresses can build to the point where they overcome the strength of the rock, leading to sudden failure. This process is inherently irregular, making intraplate earthquakes difficult to predict both in timing and location. The depth of the event also plays a critical role in determining its characteristics. At 10 to 11 kilometers below the surface, the rocks are under significant pressure and temperature conditions, yet still within the brittle regime where fracturing can occur. Deeper earthquakes tend to involve different mechanisms, often related to ductile deformation. But this event falls squarely within the range where classical fault slip dominates. The relatively shallow depth contributes to the efficiency with which seismic energy is transmitted to the surface, even if no visible rupture occurs. In terms of energy release, a magnitude 5.5 earthquake represents a substantial but not extreme event. The logarithmic nature of the magnitude scale means that each increase of 1 unit corresponds to roughly 32 times more energy release. As such, while this earthquake is significantly stronger than smaller, more frequent events, it remains well below the threshold associated with widespread structural damage in most contexts. Nonetheless, its occurrence in a stable continental interior adds to its significance from a scientific standpoint. Monitoring agencies continue to analyze data from the event, including waveform records from seismic stations distributed across Australia and beyond. These data provide valuable information about the propagation of seismic waves, the properties of the crust, and the details of the faulting process. In regions where earthquakes are less common, each event offers an important opportunity to refine models of seismic hazard and improve understanding of the underlying geology. The broader pattern of seismicity in Central Australia is characterized by infrequent but sometimes notable earthquakes. Historical records include several events of comparable or greater magnitude, indicating that while the region is not highly active, it is not entirely inactive either. Instead, it exhibits a form of intermittent seismic behavior driven by the slow accumulation and release of stress over long timescales. As data continue to be collected and analyzed, attention remains focused on the mechanisms that allowed this earthquake to occur where no obvious fault is visible at the surface. The interplay between ancient structures, present-day stress fields, and the physical properties of the crust forms a complex system that is only partially understood. Each new event adds another piece to this puzzle, contributing to a more comprehensive picture of how stable continental interiors behave under stress. Attention has increasingly shifted toward the deeper structural framework beneath Central Australia, as additional seismic data from the magnitude 5.5 event continues to be processed. The absence of a clearly defined surface rupture has directed focus toward subsurface imaging and waveform inversion, both of which help refine understanding of how stress is distributed and released within the continental interior. Subtle variations in seismic wave arrival times across monitoring stations reveal heterogeneity in crustal composition, suggesting that the rocks in this region are not uniform, but instead consist of interlocking blocks with varying degrees of rigidity and strength. This variability plays a critical role in how seismic energy is both generated and transmitted. Areas composed of stronger, colder rock tend to store elastic strain energy over longer periods, while weaker zones may deform more gradually without producing significant earthquakes. In Central Australia, the crust is generally old, thick, and mechanically strong, allowing stress to accumulate over extended geological timescales. When failure eventually occurs along a zone of weakness, the resulting rupture can release energy efficiently, even if the overall displacement along the fault is relatively limited. Detailed examination of seismic waveforms from the event indicates a relatively simple rupture process, consistent with a single primary slip episode rather than a complex sequence of cascading fault movements. This is typical for moderate magnitude intraplate earthquakes, where the rupture area is confined and does not branch extensively into multiple fault segments. The estimated rupture length is likely on the order of a few kilometers, with displacement measured in centimeters rather than meters. Despite this modest scale, the rigidity of the surrounding crust enhances the propagation of seismic waves, allowing the event to be detected across a wide network of instruments. The orientation of the possible fault planes, as derived from the moment tensor solution, aligns with broader patterns observed in Australian intraplate seismicity. Reverse faulting mechanisms dominate much of the continent's interior, reflecting a persistent compressional stress regime. This stress is thought to be influenced by forces acting along the northern and eastern margins of the Australian plate, including interactions with the Pacific and Eurasian plates. Although these boundaries are thousands of kilometers away, the stresses they generate are transmitted inward through the plate, gradually concentrating along pre-existing zones of weakness. Geodetic measurements, including satellite-based positioning systems, provide additional context for this stress field. While the Australian continent is often described as stable, high-precision measurements reveal that it is continuously deforming at a very slow rate. Horizontal motions of a few millimeters per year can accumulate over millions of years, contributing to the buildup of stress within the crust. These movements are not evenly distributed, and certain regions experience higher strain rates due to the presence of ancient structural features that focus deformation. In the vicinity of the Musgrave Block and the Petermann Ranges, the crust has undergone multiple phases of deformation throughout geological history. The Petermann orogeny, followed by the Alice Springs orogeny imposed significant compressional forces that reactivated older faults and created new ones. These events left behind a network of deep faults, folds, and imbricated structures that extend into the crust. Although these features are no longer actively forming mountains, they remain mechanically distinct from the surrounding rocks, making them more susceptible to reactivation under present stress conditions. One of the challenges in assessing seismic hazard in such regions is the limited visibility of these structures at the surface. Unlike active plate boundaries, where faults are often clear and well mapped, intraplate faults may be buried beneath layers of sediment or eroded beyond recognition. This makes it difficult to identify which specific structures are capable of generating earthquakes. In many cases, seismic reflection and refraction studies are required to image these features indirectly, but such data are not always available at the resolution needed for precise mapping. The depth of the earthquake, estimated at approximately 10 to 11 kilometers, suggests that the rupture occurred within the upper part of the continental crust, where brittle behavior dominates. At greater depths, higher temperatures and pressures tend to promote ductile deformation, reducing the likelihood of sudden fracture. The transition between brittle and ductile behavior is not fixed but varies depending on local temperature gradients, rock composition, and the presence of fluids. In Central Australia, the relatively low geothermal gradient contributes to a thicker, brittle layer, allowing earthquakes to occur at depths that might be less common in more thermally active regions. Another factor influencing the behavior of the fault is the presence or absence of fluids within the crust. Fluids can reduce the effective normal stress on a fault, making it easier for slipping to occur. However, in old crystalline terrains like those found in Central Australia, fluid availability is often limited compared to younger, sediment-rich basins. This suggests that higher levels of stress may be required to initiate movement along these faults, contributing to the long intervals between significant seismic events. Aftershock activity following the main event provides additional clues about the geometry and extent of the rupture. While early reports suggest that aftershocks have been relatively sparse, this is not unusual for intraplate earthquakes. The limited extent of the rupture zone and the strength of the surrounding crust can constrain the development of secondary failures. Nonetheless, continued monitoring is essential, as even small aftershocks can help delineate the orientation of the fault plane and refine models of the stress field. From a hazard perspective, the occurrence of a magnitude 5.5 earthquake in this region underscores the importance of considering low probability but potentially impactful events in areas not traditionally associated with seismic risk. Infrastructure in Central Australia is generally designed with minimal seismic considerations, reflecting the historically low frequency of earthquakes. However, the efficient transmission of seismic waves through the rigid crust means that shaking can be felt over large distances, potentially affecting communities and facilities far from the epicenter. In addition to ground shaking, secondary effects such as minor landslides or ground cracking cannot be entirely ruled out, particularly in areas with weaker surface materials or steep local topography. However, the remote nature of the epicentral area reduces the likelihood of widespread damage or disruption. The primary significance of the event lies in what it reveals about the ongoing dynamics of the Australian plate and the capacity for stress accumulation within its interior. Long-term seismic records indicate that Central Australia has experienced similar events in the past, though they are separated by extended periods of relative inactivity. This pattern reflects the slow pace at which stress builds within stable continental interiors. Unlike plate boundary regions where tectonic motion is more rapid and continuous, intraplate regions may go centuries without significant earthquakes, only to experience sudden releases of energy when conditions align. Advances in seismic monitoring technology are gradually improving the ability to detect and analyze these events. Dense networks of digital seismometers, combined with real-time data processing, allow for rapid determination of earthquake parameters and more detailed study of rupture processes. In regions like Central Australia, where data coverage has historically been sparse, these improvements are particularly valuable. The integration of seismic data with geological and geophysical information is essential for developing a more comprehensive understanding of intraplate seismicity. By combining observations from multiple sources, researchers can better constrain models of crustal structure, stress distribution, and fault behavior. Each earthquake contributes incremental knowledge, helping to refine assessments of where future events might occur and how they might unfold. As analysis of the magnitude 5.5 earthquake continues, attention remains focused on the broader implications for continental dynamics. The event serves as a reminder that even the most ancient and seemingly stable landmasses are subject to ongoing forces that shape their structure over time. Beneath the quiet surface of Central Australia, stresses continue to accumulate, guided by the legacy of past tectonic events and influenced by present-day plate motions. This evolving understanding does not point to an immediate increase in seismic risk, but highlights the importance of maintaining awareness of the underlying processes at work. The interplay between ancient geological structures and modern stress fields creates a complex system in which earthquakes, though infrequent, are an integral part of the natural behavior of the crust. As more data becomes available and analytical techniques continue to advance, the picture of what triggered this event will become clearer, offering deeper insight into the hidden forces shaping the Australian continent. The significance of this earthquake extends beyond its magnitude, providing a valuable case study in how energy is stored and released within one of the world's oldest and most stable tectonic settings. If you found this breakdown informative and want to stay updated on major seismic events and the science behind them, make sure to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.